one specific facet of the systemd project. Systemd is this big suite of different components that you need to build an operating system from, and we'll focus on one little component of it, which is incredibly useful, but very little known, and everybody should know about it. I've been frequently doing talks about systemd, and usually I try to, do the big picture talks. This time I thought about just talking about one specific little tool out of it, because I think everybody should know about it, particularly administrators, or people who build software, or people who test software, people who, I guess everybody, what nowadays is called DevOps people, should know about this, because it's actually incredibly useful if you deal with containers, if you play around with building container images to then ship on servers and things like that. But also if you're a developer and try to quickly build something for a different distribution, or test something on a different distribution, or things like that. Usually I talk relatively fast. If you have any problem with that, please just show up and I'll try to slow down. If you have any questions, please interrupt me right away. Right? Just show up. I much prefer if we could make this an interactive session rather than something where I just keep talking, then everybody asks questions in the end. So yeah, interrupt me. Yeah, I assume that everybody of you knows the change root command on Unix. Who knows it? Show it. It's actually the first time I ever asked people that question like that on a talk. But yeah. So let me rather ask, because everybody actually showed up, does anybody not know change root? Okay, everybody knows. So I guess I'm at the Linux conference here. So yeah, systemd-nspawn is basically the same thing as change root. It's just so much nicer. So yeah, let's start by discussing why it is actually part of systemd. So I mean, systemd, as mentioned, is nowadays, I mean, it started out as an init systems, and most people probably consider it one, and that's the end of the story. But it's actually much more than that. It is for us basically this suite that we build an operating system from, which I already mentioned. So it will contain everything that you need, that we think are absolutely essential for building of most operating systems, regardless if it's for embedded, for servers, or for desktop machines. Just a couple of components that we think that deserve being nicely integrated and kind of make use of what the Linux kernel provides and work well together. While doing this, of course, we look at the various components of the Linux kernel that already exist and try to figure out if they're actually in any way relevant to systemd or not, or if it's some specialist feature. In some cases, especially in the container case here, we saw, okay, all the container stuff is actually not that hard to use from what the kernel exposes, and we would like to integrate it more with systemd. However, currently there was, or when we started looking at it, there wasn't really such a nice tool to play with it. Container stuff on Linux usually means LXC, or means libvirt LXC, which by the way are completely different projects, and maybe OpenVZ and these kind of tools. All of those are written primarily, I guess, for distribution of things and servers, right? They are relatively comprehensive. They expect a relatively high degree of understanding of what's actually going on. They are, in a way different than good old change root is, because change root, everybody can use that, right? Every administrator on his home machine, if the machine doesn't boot, or if he then boots up with some USB disk and then wants to get back onto his home machine, he's totally capable of using change root. He just knows how it works. These other tools are certainly not that like. So, because we actually develop operating system, we thought, okay, we need something like a tool that just makes use of this kernel facilities and makes it really dead easy to use, just for our own testing purposes in the beginning, because we wanted to make sure that the entirety of systemd should work equally well on a bare-bones system, in a virtual machine, and in a container. It should just work, right? Like previously, if you ran systemd or something inside of LXC, you probably, or especially as this finds in it, you had to make quite a few changes. Like you would have to disable the geddes and these kind of things. Because we wanted to make sure that systemd ran nicely inside of containers, we actually were looking for a tool to actually test that. And so we actually started playing around. Okay, LXC, kind of nice, but very complex. Like, for example, it exposes all the C group's attributes and all their complex complexity to the user, even though that in many cases doesn't even make much sense. Like, for example, they expose, like if you want to grant access or take away access of a container to a device node, you specify that by a major and minor number. But the thing is, major and minor numbers are not stable in the current kernel, so you cannot actually write a configuration file that will survive the boot, right? Because basically the assignment of the major and minor numbers is not defined. It's on every boot it might change. For a couple of devices like def null and def zero and these kind of things, it's stable, but it's not for hard disk, for example. It really depends on the order how things get probed by the kernel. So yeah, all these tools appeal a little bit to low level, and knowing the backend of it, like the actual kernel system call, we thought, okay, we can just write a tool that does exactly what LXC does on the lower level, but it's as easy to use as change root. And that tool is what we call systemd-nspawn. So it's called the N stand for namespace, because it makes use of the Linux kernel namespace feature, and spawn means, yeah, because it can spawn. So that's a little bit the background story why we added to systemd. Now, people could assume that it's kind of like a competitor to LXC or Liquid LXC, and we clearly want to tell already it's absolutely not. We push nspawn, like we created nspawn for our own users, and we try to get people to use it for testing, for debugging, for profiling, and for building things, right? Like, if you actually ship something on the server, you should not use this. It's not the tool that you want to use there, because it doesn't have any management things and stuff like that. It is, as such, really the thing that, like the same way as you would not, or probably not, and hopefully not, ship something on the server that just uses the user bin a change root command. The same way you shouldn't ship something on the server really that runs nspawn. So, in that regard, it is just another tool and a powerful tool set that you have nowadays to run containers in Linux. Yeah, if LXC, I mean, just a little bit of background, but yeah, if you want to know more about the LXC, Liquid LXC, and kind of things, then probably the other conference that is in parallel is probably more interesting. But just a high-level overview, like what people, in case you do not know that yet, what people always confuse the fact that LXC and Liquid LXC has nothing to do with each other. Basically, they use the same kernel interfaces. Since nspawn also uses the same kernel interfaces and does not share code with either LXC and Liquid LXC, basically the relationship between LXC and Liquid LXC is the same as between LXC and nspawn and Liquid LXC and nspawn, which is there is no relationship except that they use the same underlying kernel. I think actually here LWN has actually pushed out a couple of articles about the underlying kernel stuff. So if you actually want to know what's actually below LXC, Liquid LXC, and nspawn, you can read those articles. Yeah. So again, it's not about shipping something on your server. It's not about actually using that in production. It's about building stuff. It's about testing stuff. It's about debugging stuff. And it's about profiling stuff. And there are actually a couple of distributions which nowadays use that for setting up the build environments for packages. Because basically with very little work, you can set up a container and then you can put it up and it will just work. So the entire idea of systemd-nspawn is that there is no configuration. The same way as there is no configuration for change root, right? Like if you want to start your change root machine, you don't configure anything, right? You just invoke change root and then the directory will change root to that. The same is the idea with systemd-nspawn. There is no configuration. It's the thing that just works. Well, sorry at least. The thing though is that to make it just work, there are a couple of bugs currently left, at least on the Fedora 19, or actually the Fedora 20 that I'm using here, where we actually run into 2 bugs that are still a bit nasty, but I will tell you how to work around them. And I assure you that probably F21 at least will have all of them fixed, and the final version of F20 will have most of them fixed. So yeah, that's a bit yeah, basically telling you that it requires no configuration, just works, actually doesn't. But yeah. Again, not for deploying, use Liquid LXC or something like that. So, the essence, like basically everything I want to talk about in this talk are these 2 commands, like the upper one and the lower one. The upper one is doesn't have to do anything with systemd-nspawn. It's just the configuration line that you need on Fedora machines to actually create a minimal Fedora installation inside a subtree. So it uses yum, it uses -y just to say that it should always say yes. You pick a version, you say we don't want signing because I was too stupid figuring out how the signing works if you build a container. you say where you want it installed, like this is the root for the container. You say, yeah, basically disable everything except for Fedora itself, and then you install the base packages and that's it. After you've done that, you actually have a directory there, and it looks exactly like a normal Fedora installation. It doesn't have a kernel though, right? Like these are the dependencies of this package is what you installed, not a kernel. And that's good that way, because for a container you don't need a kernel. And then, yeah, of course, this is the Fedora-specific command, which is yum, of course. The equivalent exists, of course, for Debian, where it's that bootstrap, and there's something for Arch Linux, and there's something for the other distributions. The man page of systemd-nspawn will actually help you with that, and we'll just show you the one line that you have to type. So if you're actually looking for the counterpart of this for your specific distribution, just check the man page. It's all in there to make it really super duper easy for you. So after you type that, you have the image, and with this command, you can actually install it. Right? It looks a lot like change root. You specify the path to it. The -d means specifying the path. If you don't specify the -d, it will basically start the operating system that's your current working directory. And the -b, then the lowercase b, basically means that the machine should be booted up rather than just getting a shell. Right? If you traditionally just use the change root command, it will just give you a shell. It will not boot up the machine. So if you look at this, the basic difference at this point is mostly this can be used to actually boot up the full container as if it was a real machine. So now we have seen these commands and actually try this because I didn't want to rely on the network here. I actually already did the first part, so you have to trust me on that. One of the bugs that they actually still left is actually in Fedora, so that actually this command will break you something with /var and /run, but that's hopefully fixed soon. But anyway, it's really the goal that this actually will work. So let's do this. I have prepared, as mentioned, this yum command to get the directory set up. I hope everybody can see the font. I think so at least. I prepared that as my home directory in the Fedora tree. If you go in there, then you actually see, yeah, it looks like a real Linux in there, right? It's sitting in my home directory. It's created by yum. I actually have the same thing here because I need that for testing with Debian. So in the Debian tree directory, I have the equivalent with that bootstrap. Since that bootstrap is actually packaged for Fedora, I could just do that trivially on Fedora. Just as a thing that I mentioned was it was the man page. If you go to the man page and go to the end of it, then you can see the examples. Yeah, see the upper one. The upper one here is the yum command that I just showed you. Unfortunately truncated here, but let's scroll to the right so you can see that. Here you see the equivalent commands for Debian. Then you have the equivalent command for Arch Linux. And the other ones that do something different. But anyway, so just to show that. So I've already prepared that. So then let's do that. Let's actually load, can you see that? You can. This directory. So I'm using, since I installed it to a different directory, I had to slightly modify the command and it actually specify the real directory. And then I can, this has to be done as root, the same way as change root has to be done as root because the functionality of the kernel is not available if you're not root. Then we have authenticated, and there we go. I'm already logged in. So if you look at this, oh no, now actually it started the Debian machine, sorry, because it's specified the Debian tree. So sorry for the confusion. But anyway, you see here, you get the normal message that you would get if you boot Debian nowadays. You're like, welcome to Debian from Linux, sid. It's a relatively old version of systemd running inside of the container. Like in this case, systemd-44, it's ages old. But there you go, you have your virtual machine, we can power it off again. And the thing that I actually wanted to do, which is start the Fedora tree, where you get it like this, right? And if we scroll up to see what actually happens, it's a little bit cleaner here. You get the welcome to Fedora 19 thing, which you see on a normal bare machine as well. And yeah, this is just because we didn't specify anything to try to boot actually into graphical mode. But it doesn't really matter because there was no GDM installed. It doesn't even work having GDM installed in there because there's no hardware available in the virtual machine. But anyway, and then you see the normal boot process of Fedora, and then you can log in, and you get a shell. Now you're inside the container here, so if you type ps, then you actually see the processes here, and because you don't see the host processes, you see systemd here, journald, dbus, system login, and your actual login shell. Otherwise, there's nothing installed, so you can't actually type anything. Since this is a full container, you can install software inside of it and do whatever you like. Yeah, it's a full blown machine. I can power it off. I can. Okay, this is actually one of the bugs that's kind of in the kernel.
Would you say more about this bug?
About this bug?
Yes.
Okay, so I mean it's a little bit off topic because this bug shouldn't exist, but it's there. It's a bug in the kernel. It's basically we in some cases do not get the notification of the kernel that a container really terminated, and because we don't get that that notification, the container basically stays around all the time. So in systemd, every container that is running, regardless actually if it's an nspawn container or a libs.lxc container, carries a name, right? That name is attached to all the process of it, so that you can actually see it with PS and things like that. And that name is never freed again, right? And if you do not specify what I'm adding here now, -m and some random words, then it will generate this name for the container from the directory that you have specified here, which in this case it would take the Fedora tree stuff. But since the Fedora tree container didn't get cleaned up because the kernel's bug didn't send us a notification, we just pick a completely random bullshit name here, which is in this case is FFFFFF, and then we can boot it up again, right? So yeah, it's unfortunate that there's this bug, and I need to isolate the bug. Like I've talked to Tejun, who's like the Figo maintainer where this problem lies, and he's kind of waiting for an isolated test case for this so that we can actually get it.
What do I see if I do a PS3 outside the container?
Let's just do that. So let's first do that inside the container. Okay, we don't have PS3 in the container, and I don't have network, so I can't install it, sorry. But let's do it outside of the container. I hope I have it installed here, yeah. There we go. It's a bit hard, a bit difficult to see here. That's less. So that's where you see it. There's the ground channel and bash. No, where is it here? It says in the nspawn. You see that these are child processes of that.
I can fully see inside. I can fully see inside.
Yes. It's basically like any other. I mean, that's not a particular property of nspawn. That's a particular property of all the containers that we have on Linux. Basically, everything that we run in the container to the outside appears as if it was just a normal child process. Of course, what you will notice, I mean, you don't see it here, but the PIDs will be different, of course, right? Because this process here is the PID1 of the container, so everything appears differently. So if we type PS on the host and pipe that into less, then you will first see this is the systemd of the host. But then if you actually go down, so where is it? There you see the other systemd, and this one has something that is not one. But if you do it inside the container, which we can totally do as well, and then you see that's actually the same process. This one, it's called PID1 here. From the outside, something different. Yeah, but actually, since we actually looked into this PS tree, the PS tree it doesn't really show you that this thing is a container. We offer an alternative to PS tree, which will not show you the hierarchy of the processes, but will actually show you the hierarchy of C groups. I'm not sure if you guys are aware of the C groups feature. If you are aware of what that is, then I'm sorry, because I will give you a little bit of introduction to that. C groups is basically, it's a much discussed feature of the recent Linux kernels. It's basically something where you can take a couple of processes and make a group out of them, a C group out of them, a control group out of them, and which is basically just this group of processes. You can attach a label to them, like a name. You can organize these in hierarchical fashion, so you can have a tree of groups, and then you can optionally apply resource limits to them. It is one of the basic building blocks of what Linux containers are built of, right? You take the processes of the container, you put the label on it, you possibly add resource management to it. That's basically what C groups are. C groups, as mentioned, are organized in hierarchy, and we can actually easily show that. Systemd comes with a tool called CGLS, meaning C group list. If we type that, then we actually see the C group hierarchy of the system. It's an incredibly useful command. It really reminds, it looks a little bit like PS3, except that it totally does not. So you basically see all the C groups here. There's, in this case, there's a slice. I'm not going to go into detail what a slice is because it's very systemd specific. Let's just say every user gets a slice, every login session of the user gets a slice here. So every user 1000, that's me, and then I got a session. And these are all the processes that are running inside of it. And if we then go down, they are the process IDs, that's true. So, and here, you see the machine scope. That's actually the thing that we created. And then you have actually, like basically this subtree here that you see from there to there is the same thing, that is the entire thing, just for the container, if you follow what I mean. So because I'm logged in once, I have one user thing and I have one session inside of that, you will see that. And then in system you find everything that is basically system. Everything like daemons and stuff like that. And for every daemon you have one C group, and inside of each of those C groups you have the process of this daemon, and that's in this case pretty boring because it's just one process each. But anyway, so the takeaway of this is, if you run this, you can type systemd-nspawn-linuxcon-eu-2013, and we'll actually show you the hierarchy of the system, how it consists of login sessions and machines and services. And then you can hierarchically go down for that and then go further down into the individual containers. Systemd-nspawn, again, is in no way tied to systemd-nspawn. It works for any kind of C group setup, right? And it's particularly interesting if you have containers because then you actually can go down. We need to go further down and stuff. But it's an incredibly useful tool. There's a similar tool actually called systemd-cg-top. So CGLS just gives you a directory, like a plain list of all the C groups with what's contained in that. Systemd-cg-top will actually show you the resource usage of this. In this case, we unfortunately, because the window is too small, can't really see the stuff that's inside of it. What the fuck is that?
You didn't background representation in the shell.
Yes.
Oh. Yeah, that's a good explanation. Yeah, but I don't want to unbackground it down. Anyway, so cg-top, I think this goes a little bit too much into a different topic, which is resource management, because it will actually show you the resource management, like the resource usage of these services, because we don't have any resource usage in the container right now. Because there's nothing actively running, you don't see it in the CPU thing there, so it's kind of a stupid demo that I just did because you actually don't see the container there. But anyway, let's ignore that for now. Let's just focus on CGLS and how awesome it is, and actually shows you the recursive things of everything. Let's go back. Okay, now I have to terminate the other container, this one. Okay, I first have to power off the container. By the way, you can even reboot and all these kind of things. It will just work, it will just appear everything. Something that nspawn, by the way, is very good at is that it will automatically inherit the network configuration of the host, which is systematically different from how libvirt, LAC, and these kind of things usually are set up. Because basically, we copy the etc resolve conf of the host automatically into the container so that everything just works. We do a couple of other things to make things just work. Like, for example, the time zone is automatically synchronized from the host into the container, so that the timestamps look nicely in the container. You don't have to set anything up. The idea, again, is that with that yum command, you set up the container, and when it's systemd-nspawn, you can just boot it, and it will just work. Let's go back to that. Okay, now I have to do this. There we go. Again, this is like the most important slide of them all, because it actually tells you how to do this. If you're wondering how, again, just remember systemd-nspawn, go to the man page, you find this line, and you find this line. By the way, again, if you guys have any questions at any point in time, totally interrupt me. Okay, the next command I would like to talk about is machine control. Machine control is again something that is incredibly useful in context of systemd-nspawn, but is not bound to systemd-nspawn. It's supported with libvirt LXC the same way. Basically, in systemd, we wanted to make sure that containers are nicely integrated into the rest of the OS. The basic idea there is that on Solaris you have these concept of Solaris zones, which are relatively nicely integrated into the rest of the Unix commands. Like for example, you can list the services on your local machine, and then you can actually recursively go down and also see the services with the same command of all the containers that are, all the zones that are running on the same host. We are interested in providing the same kind of integration on Linux. So far, the container worlds and the rest of the operating system were pretty isolated. We wanted to make sure that they're nicely integrated. Nicely integrated, for example, means that if you type PS, where you, like, you know PS, right? Like where you see all the processes, the name of the process, PIDs and things like that, and you can show all kinds of attributes. We wanted to make sure that you can also show the container name a process belongs to, because after all we have seen in the PS tree, you have all these processes all there in the host, and you see this gigantic tree of things coming from all the containers. What you really would like to know is what it actually belongs to. For that, we created a little bit of a mini daemon, like mini service that just activated if people need it. All it does is make sure that if some container manager, like systemd-nspawn or like libvirt-lxc runs, it will tell the system that. The system will remember that, and it will provide this functionality for PS and things like that to actually show you those columns. All that works already, at least if you run Fedora 20, so that you can actually, yeah, if you type PS, you can actually get the columns for to which container that works. Again, this works for libvirt-lxc containers as well. However, I can show you how this works here for nspawn because it's so much easier to do. If we type machine control right now, because of this bug that I mentioned earlier, the machines will not have been cleaned up. So if I type this, you actually still see them running there. The reason why we call this machine control, by the way, it probably deserves a little bit of an explanation. We wanted to make something work that is capable of recognizing processes which belong to containers the same way as recognizing processes which belong to virtual machines, like VM or KVM or something like that. So we try to come up with the names that are generic enough to cover any kind of virtualization technology, regardless if it's more like virtual machines, like running a kernel inside of the thing, or more like containers running the things on the shared kernel. And the name we came up after looking for a long time is machine. It's basically the generic thing for that. Yeah, in this case, you see the list. As mentioned, they're actually dead, but because of the kernel, they didn't learn that they're actually dead. So the original one was Fedora 3, and then I renamed it to start another time. It's FFF, still running. This one says basically this column is if it's a container or a VM. Since we did not start a VM, we don't have an entry there, so everything says container. And then services, like just a little bit of information about what actually started there. So machine control can give you a list of the current stuff, and these, like if you type PS, but actually I don't know the problem is I would like to show you that how that looks in PS, but I don't know the precise command line. So yeah, let's see that's the machine column. So let's try that. I hope this will work. So it ate that, so then let's start the container again. And let's give it another name. And so this is this thing running now, and now let's try PS. See, and okay, it doesn't look that nice because I manually put together a couple of columns here. But if you use this is standard PS again. You see we say we want to have the list of the processes with the PID in the first column, with the arguments in the second column, and with the machine name in the third column, and then we see, okay, these are the ones that actually belong to the machine. If we run a couple of containers at the same time, this of course gets more interesting as we will have more processes that actually have listed something in the third column. If there's nothing listed in the third column, this means that it's either not assigned to a container that's actually of the host, or that the software in question doesn't actually tell systemd about machines. libvirt-lxc tells systemd about machines. Not libvirt-lxc, like the non-libvirt-lxc, the project that's just called LXC, doesn't do that to my knowledge as far as I know. I guess in a way, Yeah, we work very closely together with the libvirt-LXC guys. The LXC people are a little bit more distant, so the updates don't happen that quickly. Anyway, so machine control, let's continue with that. If I type machine control right now, we see the 3 machines. Actually, one of them is currently running. Again, the other ones are because the kernel doesn't tell us that I stop. You can actually use a couple of commands on that. Like, for example, we can do machine control status on this third machine because we run it as the most interesting one. So if you run that, you actually get a lot of more information. Like, for example, you know the PID of who started that, like who's the PID 1 of the machine. In this case, it's systemd because the container internally also runs systemd as init system. Then you see that it was nspawn that registered it, and you know that it's the container and not the VM. You have the information about what the root direction actually was. And you have the C group contents basically with everything that's running inside of it. So all of this is also viable as a lower level command with machine control show. So yeah, the stuff that is exposed to is actually the machine control is nothing but a very test case for us because we provide APIs how people can actually enumerate the machines that are currently running, right? The containers and virtual machines. And this tool is basically just the front end for that. There's also a couple of dbus interfaces, like you can. It's basically like, yeah, it's a generic way how you can list, regardless what machine manager is used, what containers are there, and actually do a couple of operations on it. Yeah. So that's machine control for you.
Listening, is it not showing? Is it because it's a Fedora 19 image that you're fixing that it's not showing scopes and slices within it? Would it show the scopes and slices within the, like when I think when you did a CGLS hit?
Well, I'm not logged into this one, but if I log into this one, and shit, and now I go to this shell again and I do it. Where did this command go? Maybe let's do it again. So you actually see the scope there. Just about logging in, actually.
But that's not actually split out into slices and scopes.
Oh, it is. This is a slice and this is a scope.
Ah, right.
Okay, so what might be misleading is the fact that here it doesn't have a slice thing, that's because it's a slightly old Fedora 19 and not Fedora 9. Yeah, machine control is a very powerful. Actually, if you use directly, very useless, but also like it basically exposes a subsystem to other programs that are incredibly useful. The same information is actually also available in GNOME System Monitor, like this PS-like tool that GNOME has. So if you ever feel like browsing your containers with GNOME tools, then you can totally do that and you will see the same information. Still no questions at this time? Or last question?
Is this information exposed to dbus? So basically, the machine control just queries dbus and output.
Yeah, it's a tiny dbus service that just keeps track of what nspawn and libvirt-LXC and potentially in the future LXC tell us, so that we then can hand it out to PS and all the other tools. Like our goal with something that we're probably going to add very soon actually is that system control, system control is the primary interface, how you can start and stop services, learns about containers the same way. So basically that you can just issue system control -m for the machine name, and then you can issue commands instead of on the host on a specific container of your choice. And also the same thing that I mentioned earlier with Solaris Zones, where you could get a recursive list of what's running on the host and what's running on individual containers. That's the same thing that we then will provide, basically by simply enumerating all the machines that are running and going into every single one of them and inspecting the state. And then, yeah.
So you mean the outer system control could then order what to do to an inner system control? Right?
Yes. Well, I mean, to systemd inside. So basically, the machine control that you run on the host is a front end not only for the systemd on the host, but also systemd on the many containers that you might be running. And with that, we have something that starts to feel a little bit like what Solaris Zones can do. Yeah. Again, there's 3 bugs. One you already mentioned, you saw, which is this kernel bug that we don't get the notification if the sequence entity, which is definitely fixed by the time Fedora 20 is out. The second one is the audit system is still incompatible with this entire scheme. So you actually have to turn off the audit system in the kernel. If you don't do that, then you cannot log into your containers. It's because audit is doing weird things. There's a patch for that, but it's not fixed yet. To turn it off, auditing, you don't have to recompile anything or so. All that you have to do is that you on the kernel command line specify audit equals 0. Again, this is something that will be fixed soonishly, and the patch already exists. And what was the third one?
Temp in Fedora. Var temp.
Oh yeah, the var temp thing in Fedora. Like I mentioned that already. Like the yum command will currently not create a working image for you. Because it forgets creating a symlink from var run to run, which is the bug which Fedora needs to fix. But with that one, yeah, if you have all these three things fixed or worked around, then everything works without configuration. Yeah, right. So yeah, I'm making basically the promise here that everything will be awesome in the future, but it's not yet that awesome. Yeah. Another thing that is actually kind of nice to know, if you run systemd-nspawn, then you can actually, if you run it with a default command line, it will actually create a symlink between the host journal directory. In case, I mean, does anybody not know the journal? The journal? Everybody knows the journal? There's somebody who doesn't know the journal. So the journal is basically it's an indexed logger that systemd includes. It's basically, I mean, yeah. I can do talks about journal of its own, but it's a very useful index database of everything that happened on the system, and it's a little bit like classic Unix syslog, except that it's indexed. And it's yeah, it is what we can do with a journal. What you can't really do that nicely with syslog is that we actually can interleave multiple journals from different hosts with one command. So what we can actually do here is okay, it's actually, I hope this actually works. Okay, this one is really okay, it didn't work in this case. Sorry for that, it's probably a permission problem, and I'm too lazy to debug that now. If you, yeah, that didn't work. Anyway, that's a permission problem, I'm pretty sure. But maybe we can work around that permission problem. No, we couldn't. Anyway, the idea basically is that the same way as we try to integrate system control on the host so that we can issue operations not only on the host itself but also of all the containers, and then we can do the same for journal control. And so basically there's this journal control switch -m, and that means merge, and it basically merges all the journal files of containers running on the system into one single stream. So if you use journal control -m, you can look at the stream of logs the same way as you would look on a stream of logs from your local server, but it would actually include everything that happened on the system, regardless in which container, things like that. So system control nspawn supports that. Maybe I can set that up by default, except that it didn't work in this case for permission problems, but I'm too lazy to debug that here in front of you now. Something else that might be nice to know, systemd-nspawn, as mentioned by default, make sure that the network configuration of the host is inherited into the container, simply to make it as easy to use to get started. And that in this case means that it will, like all the network interfaces available on the host are also available in the container, and etc resolve conf is copied from the host into the container to just work. You can also use in a different mode where you basically specify the command line switch systemd-nspawn-private network. If you do this here, you basically, if you specify this stuff, then instead of actually getting access to the real network, you get a private loopback device and little else, so you cannot actually get out of the container, which is ideal for build systems, because build systems usually they download everything from the internet to set up the images to build things from, and the sources from the internet. But then again, while they build, they probably shouldn't phone back to the vendor who did them. So you can actually turn that off really nicely. Just because we've seen this here currently, a couple of other features of systemd-nspawn, like the D and the B is the ones that you already saw, that you actually can specify the directory you want to put. If you do not specify the D, then you get a shell. I can quickly show that, I guess. We have. So let's pick an even different name. This was with the B was where we actually boot the entire thing. And if I drop the B, change it to a different name, then I get a shell. Right? And in that shell, there's nothing running except dash and pf. So it's basically running. It's basically as if you would boot a real system with init equals -h on the current command line. But let's shut down this thing again and have a look at this again. So -u you can actually change to different user ID inside of the container, which is sometimes useful for executing stuff. By the way, you can actually add a couple of commands here to the end. Like if we do this, I could actually invoke ls at the end. Even different name, and then you get the output directly back. Let's see other stuff that's there. The thing that I always use to pick a different name is the -m thing, where I just pick any name for the thing. Again, the name is that stuff that machine control shows you when listing the machine, listing the machine, and what TS shows you in the machine color. Slice is something that is relevant for, like a slice is basically a concept that systemd recently introduced in context of a C group rework. I'm not going to go into much detail for that, but basically allows you to, you basically can have a slice off a part of the available resources for a particular customer, and then you can assign services and machines to that slice, and then everything you can apply resource limits to that slice, and then yeah, it's basically counted together. So with -s, you can actually specify the name of the slice. Private network is the thing that I was just talking about. Read-only is an interesting one. It makes the root directory of the container read-only, which is kind of powerful because it allows you to, limit what the container can do. And you could actually relatively easily run a couple of containers from the same directory.
Can I combine the read-only with some extra that is not read-only?
You can actually do that. So there's the bind thing here. With bind, you can bind a directory from the host into the container, and then there's bind RO, which does the same thing but it's read-only mount. So you can actually, either you specify a single path, and then that path will be taken out of the host, or it's still available in the host, but it will be taken from the host and made available inside of the container in the same place, or you use the colon and pass the second thing, and then we'll place it in a different thing in the host. So for example, if you want to make a home directory available to the container, which won't be by default, then you can just pass --bind / /home, and then you have the home directory. Of course, this is not as good as it sounds because the user IDs might not match, right? So because the password database in the container is not the same one as the host, likely, not necessarily, you can of course have synced that manually, but if you have not synced it manually, then they won't match, and then the home directory is not as useful as it sounds, but it will probably still useful to do this --bind RO. The link journal mode is what I said here, that we actually get okay, now I know what I forgot. I never actually specified the -j. So let's give it a third try. That I actually boot up the machine. Or fourth try, actually, it's better. So, and then that's. Oh, by the way, one nice thing here is actually that the machine name that I specify, we actually pass on as the host name of the container later on. So if I on specify on -m any name I like, it will actually appear here as the host name. Yeah. Because, basically, like Linux containers support hostname virtualization, we just pre-initialize that. Like we just in nspawn we know the name, and then right before we hand off to the init process of the container, we set the hostname. And then systemd inside of the container is actually smart enough to detect whether the host name that is already set is a valid one, like in this case, or is just the default name that the kernel applies, which is none, right? So we try to be kind of smart and make sure that this name of container is something that transcends all the layers of our stack, right? Like, so that it's available. It's originally supplied by you in the command line. It's on one hand passed down into the container to be used as host name, and on the other hand passed to machine D, machine controller that we actually get a list. So how much time did I actually have? I think I got 50 minutes, so that's 5 more minutes. But I'm mostly done anyway. I actually want to show you the merging thing. And that it actually worked in this case. So now you actually see a merged output here of the journal control, of the journal logs. So basically this one is Delta, is my laptop, and this is the container that I just started. You just see that intermixed here. And this is again my host, and in this case it's kernel method because we mounted a couple of file systems in the container. Yeah, it's kind of cool actually. With this command basically, journal control -m. M again is this thing that merges all the registered machine journals into one, and E just jumps to the end of it. We'll just show you everything in one stream. Yeah, I think I already mentioned that we want to have nice integration with system control as well, so that you can apply all your operations on a couple of containers. Again, this is not specific to nspawn, but nspawn is the thing that we use basically for development. But usually Daniel Beranger, who hacks on libvirt LXC, is really good at very quickly adding similar integration into libvirt LXC. So basically, our goal there is, use nspawn on your local stuff to debug, test, build, and things like that, and then ship it on libvirt LXC, but have the same kind of integration available in PS, in system control, in machine control, and all these kind of things. And that's all I have for now. So if you guys have any questions, shoot.
Why nspawn, not Docker?
I'm sorry?
Why would I choose nspawn and not use Docker?
It's a very different tool, right? Docker is something where you can actually create operating system images, hand them out. Nspawn is a tool that's just chain root on steroids, right? So it's a different level on what you're trying to do. Nspawn in a way is very close to systemd, so it actually makes use of a lot of systemd functionality. You cannot really take nspawn and run it on something that's not systemd. The goal of the Docker people is to be compatible with everything that ever existed on the sun. Yeah, it's a different thing. Like Docker focuses pretty much on having something like a version-controlled file system that you can then hand out to people. But yeah, I mean, again, I do compare nspawn to libvirt LXC because it's very similar. It just has different properties. One easy to use, it's really easy to use, and the other one more like deployable. But Docker is a different story, right? Like Docker eventually will probably, at least in Fedora machines or so, but I don't really follow that closely, but it will probably make use of libvirt LXC eventually. But yeah, I hope that kind of answers the question.
So you said the networking by default, it just sort of shares the networking stack for the host.
True.
Yeah, and you copy the result of the front end. With the other sort of container things like for production and OpenVZ and that kind of thing, can you do the bridge networking with systemd-nspawn?
No.
It's either just host stack or...
Yes, currently at least. I mean, we'll probably add a couple of more things because we want to, I mean, again, it's not necessarily what you want for testing, building, profiling, and debugging, so it's not enough to do this way up. But we probably will add a little bit of it. We'll probably never add this masquerading and all kind of other stuff, but we'll probably add support for VATH stuff, simply because we want to play around with a couple of things. And because there are currently problems with, so our model, how we consider OS containers to look like from the inside, is basically that they never get access to physical hardware. And that most particularly results in the fact that UDEV, right, this device manager, does not run in containers, right? Systemd is configured that way that will automatically skip execution of UDEV-D in the containers. But if then software comes and wants to know what network interfaces are there and asks it via UDEV, it will say, there are no devices, go away. And of course that breaks some network management software instead of containers. However, we of course need to make that work, right? Like for libvirt LXC. So I would expect that soonishly we will have some support for VETH, simply so that we can make sure that discovery of network devices works properly in containers. It's easier for us to test. I mean, what people should understand is that testing things with nspawn is super easy, because you can actually GDB, you can strace from the host into the container, and there's nothing better than that if you're actually developing an init system, which is normally really hard to debug, because you can never, like the startup routine of the init system is incredibly hard to debug because you have nothing else running at that time that could actually attach to it and supervise it. But you can if you actually use these containers. So for us, again, the feature, like the focus of it is really debugging, testing, profiling, building, and for that we don't need so much except when we actually try to make things work like that.
So when systemd-nspawn spawns the process ID1 inside the container, what are the environment variables that the process receives?
That's pretty much empty, I think, but we can actually check that. Like if we, I mean, I don't want to lie, so let's check that better. Let's just, let's pick an even different name. I must have been like, I think machine control, because the kernel doesn't notify us about container ends, I think it must be about 16 machines now. So this is inside of the, like just a shell. And now if we do export, or so, then we, yeah, well now we don't know really what's actually from us and what's not. So this is what's in it. It's a bit hard to read. It's a path that we set. It's like, this is actually something yeah, I think I don't have any more time, but this basically, it's an unofficial standard that people agreed, like a couple of container people agreed on how the container manager can inform the container about the fact that it's running inside of container manager, and which container manager is basically an environment variable that says the container equals systemd-nspawn, where systemd-nspawn is basically identified. And we set the term, because otherwise things would not be useful. I think this comes from the shell though. And yeah. Does it answer? So basically nothing, with the exception of container and path. I guess my time's over. So I would take one last question, but if there is none, then I would thank you very much. If you have any further questions, ask the one last question. Doesn't work. So this all integrates closely to systemd, and it makes use of a lot of modern systemd features. Like it integrates really nicely with systemd. Like for example, you can take the systemd-nspawn and run it as a service, like a service unit, and then you can use resource management on the service unit to apply resource limits to the container. Right? And all these kind of integration that there is doesn't really make it possible to work it out outside of it. I mean, I'm pretty sure people could port it, but I will not support that, and it's not a trivial amount of work. But yeah, okay, then
I was just wondering now that network namespace and support being integrated in systemd-nspawn, wouldn't it make more sense to have it integrated into systemd itself? Like, wouldn't I maybe want to run a service, not in a container, inside a different network namespace?
Oh, you can do that. So what, this is not specific to nspawn now, but for system services, you can actually specify that there's a Boolean setting that you have on each individual service, whether it runs in a private network or not. Right, and if it runs on a private network, that is pretty much the exact equivalent of the systemd-nspawn-private network switch, which basically means you only get a loopback device and nothing else. It's actually an incredibly useful feature, because if you, I mean, now I'm completely off topic here, but if you use socket activation, which is a systemd feature where you can basically spawn a service depending on network traffic coming in, you can combine that with the private networking stuff, which basically means that the only way how a container or a service that you start gets access to the network is via that socket-activated socket that we passed in, and nowhere else, and nothing, which is an awesome feature, like super security, fantastic. But yeah, I don't know, it's a different topic, I guess, talking about that.